I've been telling you so far a lot about this quasi-linear Schrödinger equations. And one thing that I left aside during all of these lectures was the question of the Strickard's estimates. And I stated some theorems, but did not tell you anything about the proof. And so that's the goal of today's lecture, to give you an idea where those Strickard's estimates come from and how we go about proving them. And let me begin with the simplest setting where I have the constant coefficient Schrödinger equation with initial data u of 0 is equal to u0. And then I'll briefly remind you what the Strickard's estimates are. So we have this mixed LP norms, LP, LQ. First index for me will always be time, second will be in x. So I'm putting this here, and I'm not going to repeat this. And the indices P and Q, you have some notion of sharp Strickard's estimates, the best indices that you could put in there. And those are the indices which satisfy 2 over P plus n over Q is equal to n over 2. And then so this is for, and then PQ greater than or equal to 2, and n is equal to 2, and PQ is to infinity. This is forbidden. This is the one endpoint of these inequalities where the estimate doesn't hold. The estimate that I'm talking about in the simplest form looks like norm of the solution U in LP LQ smaller than norm of the initial data in L2. So this is the simplest formulation. One thing that you can do in addition to this, because you don't want to apply this inequality just for solutions to the homogeneous equation, often you want to have a source term in here. If you put a source term in here, then you can add here in a way that's by now standard, a bound for f, and this would be f in a dual space, dual Strickard space, LP prime, LQ prime, with the proviso that the P and Q I put in here don't have to be the same P and Q that I put in here, as long as they are on this Strickard's line. So now, returning to the context of the previous lectures, we care about proving this kind of Strickard's estimate. So our goal is to prove Strickard's estimates for what we called paradifferential problems. So our problems would look like I dt of v lambda. Lambda is a dyadic frequency parameter, if you remember, where we do the frequency localization. Plus, and then we have, if you want, a paradifferential second-order elliptic operator. So this could be something like gij localized at frequency less than lambda, jk. dj dk v is equal to v lambda is equal to f lambda. So we also want to allow a source term, and that source term you saw maybe the last two times that we have many choices for what we want to put in there. So lambda is the frequency where the solution is localized at, where the source term is localized at. The coefficients are localized at the lower frequency, and in the context that we were talking about earlier, our g less than lambda is really the function of u maybe much smaller than lambda, where U is the solution to our nonlinear Schrödinger equation. So this is part of that big bootstrap loop that we were talking about. And so we want to look at the question of whether we have Strickard's estimates for this problem. Maybe V lambda of 0 also is equal to V lambda 0. But for this very specific metrics which come from our Schrödinger equation. So why is it important that our metrics come from their own Schrödinger equation? This is an idea that has been gaining traction for more than 20 years now in nonlinear PDEs, that the sort of linearized or part differential equations that you get in nonlinear PDEs, they have a lot of structure that gets inherited from your nonlinear equation. And usually to get the best possible results, you have to use the fact that your coefficients solve their own equation. You'll see in a bit where we're taking advantage of this fact. Then maybe I should say I will eventually show you two varieties of this Strickard's estimates for this problem. One version happens in 1D, in one space dimension. All right, and in one space dimension, we have this family of Strickard's estimates for this power differential equation without derivative losses. And then in 2 and higher dimension, we have a version of the Strickard's estimates with derivative. This play an important role in the proof of our results. Maybe the other thing that I would mention to phrase this to put this into context is in the context of the results on nonlinear Schrödinger evolutions, this Strickard's estimates primarily play a role in the local well-posedness arguments, not so much in the global results. Because if you want to use the Strickard's estimates in the global results, you'd have to have them globally in time. And it's a long story about getting Strickard's estimates globally in time. The one-dimensional result, definitely not globally in time. The results in 2 dimensions and higher are global in time, but they're not used very much in the proof of those global results, with one single notable exception, the L4 estimate in 2 dimensions. So we do need them, but in a very specific context. And so maybe one way you could rephrase this power differential problems is, let's say we have a metric G, and we have the corresponding, I don't know, Laplace-Beltrami operator, and we want Strickard's estimates associated to the Laplace-Beltrami operator instead of the constant coefficient Laplace operator. And so I want to tell you a little bit of a story about how this kind of results have evolved. And maybe the first thing that I want to bring about is how do you prove this Strickard's estimates? And the key point in the proof is what we call a dispersive inequality. There's more than one way, by the way, to prove Strickard's estimates, but that's the way I choose to emphasize now. Which is that if you take the homogeneous equation, you can estimate the solution at time t by t to the power minus n over 2 times, and this is in L infinity, norm of the initial data in L1. Right? So you start with localized data, then the solution will decay at this prescribed rate. And there's many ways to, and the step from dispersive inequalities to Strickard's estimates is pretty standard. So let me tell you how you can prove these dispersive inequalities. And the easiest thing to do is to use the fundamental solution for the Schrödinger operator. And so you know that u of t is u of 0 convolved with a fundamental solution, where k of t is Cn t to the power minus n over 2 e to the power I x squared over 4t. And so what is important is that when you look at this fundamental solution, its L infinity norm is t to the power minus n over 2, and you capture the decay. So this is the very simple way to get this dispersive inequality. Unfortunately, this only works if you look at problems with constant coefficients, because that's when you can write the fundamental solution as a convolution. So what happens if instead of this constant coefficient operator you put a variable coefficient? We need to, in the first place, have a different proof of the Strickard's estimates for the constant coefficient case. And maybe let me observe that this inequality is invariant with respect to scaling. So let me just try to look at t is equal to 1, and I want to see how do I prove this for t is equal to 1. And then my initial data, u of 0, here it's in L1, but L1 is a superposition of Dirac masses, so I'll think of my initial data as a Dirac mass. All right, and then the idea is, I was telling you earlier about wave packets. I would like to take my solution with this particular initial data and split it into wave packets. And to split my solution into wave packets, we saw how wave packets are constructed. You start with this coherent state as an initial data, and then you want to, you look at the solution and hope that the solution stays coherent up to a certain time. So I want to decompose, let's say, Dirac mass as a superposition of coherent states. Which is like a superposition of some functions of the form, let's say, chi of x minus x naught e to the power I psi naught times x minus x naught. What's nice about working with the Schrödinger equation and on the unit time scale is we saw that for every time scale and for a wave packet we have a coherence time which depends on the initial localization in position and frequency. And so for the Schrödinger equation the correct scale is simply the scale 1. So this means that this bump function is just a Schwarz function. Maybe you can put a Gaussian in here, and this is on the unit scale. So this would be functions localized on the unit scale in frequency, localized also on the unit scale in frequency around the position x0 and frequency psi0. And there's two ways you can realize this decomposition. And one way is to do it discretely. And discretely, this corresponds to taking x0 and psi0 on the lattice, let's say Zn cross Zn with unit separation. And the other way to do it is to do it continuously. And this is what is accomplished using, maybe you're familiar with what's called the Bargmann transform. So this corresponds to x0 and psi naught in Rn cross Rn, and then this sum becomes an integral. sometimes Bergman transform, if you use it on different scales, is also called the FBI transform. And if I remember correctly, it has 2 or 3 more names, depending on who uses it. And so what is happening in here is you start with, and I'll show you the proof in pictures. You start with your initial data, which is the Dirac mass. And this Dirac mass, I'm thinking of it as a superposition of these coherent states. Now, one coherent state could be a bump function around the center here. And this coherent state will generate a wave packet. And this wave packet moves in the direction with the group velocity determined by the center frequency, psi naught, and will stay coherent up to time 1. So this is t is equal to 0. This is t is equal to 1. So this is one wave packet. Another wave packet will move in a different direction. Now, when I switch, so suppose I'm working with a discrete decomposition. When I'm switching from one wave packet to the next one, I'm moving my frequency by 1 unit. And then I'm changing the velocity by 1 unit. And so the place where I arrive here at time 1 will be also at distance 1 from where I had previously arrived. So that means, this is my one-dimensional picture if you want, that even though at the initial time these wave packets live in the same place, as they get to time 1, they separate completely. All right, and so if here I put some coefficients, c x naught psi naught, then all these coefficients here will have size 1. All of my wave packets will have size 1. And so I start with the Dirac mass at the initial time, which is the sum of these bumps on the scale 1. And then at time 1, I get a sum of bumps, but now these bumps are separate. Right? There's no more overlapping between them. And so obviously, if each of them has size 1, then the L infinity norm at this time also has size 1. Right? So here, these guys add up to the Dirac mass. This guy add up to u of t. And then u of t has to be smaller than 1. So this is, in pictures, the proof of this dispersive estimate for time 1. If I wanted to do the same picture on a different time scale, let's say on a shorter time scale, then, so let's say I want to go now from time position 0, from time 0 to time t, I cannot use the same wave packets. If I were to use the same wave packets, then you see that at time t, which is earlier than 1, you have a lot of overlapping between these packets. And you can still try to add them up and see how much they overlap. But if you do this, you get a non-optimal inequality. So the correct way to think about this is to rescale this picture. And what happens when you rescale this picture is the coherent states here are going to be on a narrower scale. And you choose this narrower scale so that the wave packets separate up to time t. And we did this computation maybe in the first lecture. And so this new spatial scale is square root of t. So you have narrower packets if you want to go for a shorter time. So you don't do a single wave packet decomposition, you do a multiscale if you want wave packet decomposition, if you want to get the dispersive estimate at all time. All right. Now, if you look at each individual wave packet, okay, maybe starting at the point x naught and having a frequency c naught, this moves with the velocity, which is the group velocity associated to the frequency c naught. So this is the group velocity v c naught. And in the case of Schrödinger equation, v c naught is simply 2 times c naught. So depends linearly on the frequency. Okay, so this is what happens in the constant coefficients. And then we ask, how do we make the transition to problems with variable coefficients? So now from the metric being the identity, we want to move to a variable coefficient metric, right? And so then our hope for wave packets, which previously they would move in straight lines. Now they are not going to move in straight lines, they are going to move along geodesics. Geodesics of the metric G. And the way you know that they have to move along geodesics is that you look at the principal symbol of your Schrodinger operator. So you look at Gij, psi I, psi j, and you look at the, let's say this is P of x and psi, and you look at the Hamilton flow of this symbol P, and this Hamilton flow gives, so this is P psi dx minus P x d psi, and this tells us how the wave packets should move. All right. So in order to construct wave packets, you might say, oh, you have to have some decent knowledge about the Hamilton flow associated to, in other words, about the geodesics associated to this metric. And this is where we run into problems with the Schrodinger equation. And the reason we run into problems is the following. Like you see in this formula, if I assume that my center frequency is of size lambda, then the corresponding group velocity is also of size lambda. And so as the frequency goes to infinity, so does the group velocity, which is why we say that the Schrodinger equation has an infinite speed of propagation. All right? And this means that when I'm looking at this group velocity moving our packet over a time interval, let's say, of length 1, this means that the distance that this packet should go through is very large, right? It moves with, so this means that over time 1, a wave packet should move like lambda for a very long distance. And that's bad news, right? The reason this is bad news is that even if we have the smoothest metric, that gives us control over the geodesics over a unit time. But getting control over the geodesics over a huge interval of time, arbitrarily large, because eventually our lambda has to go to infinity, we can't do this without putting so much assumptions on the metric, so many assumptions on the metric, so that the entire analysis becomes either trivial or meaningless somehow. So that's the problem. That's the main problem that you run into when you try to implement this kind of strategy for the Schrodinger equation. So you have two ways out of this.
What is the regularity requirement on the metric Gij?
To make sense of the geodesic flow, you could say C2, right?
But this wave packet, the mass is can still run at.
I'm getting to that. Right. So then we want to see how much survives somehow if we don't have to worry about the geodesic flow for these very long distances. And there are two questions to ask. One is, how much regularity do I need to impose on the metric? Okay. And the second question is, what do I, well, will I still inherit some streetcar, will I still get some wave packets and some streetcars estimates if I only want to use the local Hamilton flow and not the global Hamilton flow, right? So of the metric, that's one question. And the second question is, how long do we track the flow? And so one obvious solution to this is that we track the flow up to a distance 1, And then one easy answer here is to work with the metric of class C2, just so that we can make sense of the geodesic flow. And so this strategy, if it works, just want to emphasize, is not perfect. Because if delta x is equal to 1, and you move with speed lambda, this means how far do you get? You get to time delta t is equal to lambda inverse, right? So you can work out your parametrics only up to this time. So what do we do? First, we give a name to this time. We call this the semi-classical time scale. Okay. And then we say, well, perhaps we can make things work out and get our Strickard's estimates up to this semi-classical time scale. Okay? But that does not give us Strickard's estimates up to scale 1. This gives us estimates up to a time scale that depends on the frequency. Okay? What if I want to go to time 1? Well, if I want to go to time 1, then I foliate this in slices of size lambda inverse. Okay? And I write my estimates on each of this slice. Hopefully I can propagate energy estimates. That's easier. And then I get lambda pieces that I have to add up, and I would add up these pieces in time using the LP norm that you see in there. So you add LP norms over a number of slices, you get a loss, and you get a loss of lambda to the power 1 over p. This is our loss. So we have Strickard's estimates by this argument with the loss of derivatives. All right? So this scheme was implemented maybe about 25 years ago first. So there was some work that I did with Stafilani. And the context we considered was the case where we have the Euclidean metric outside the cylinder and the perturbation of the Euclidean metric inside the cylinder, so that when you have a geodesic, each geodesic spans only a distance 1 inside the cylinder. So that's exactly the context that I have been describing. And then another direction here, which was pursued maybe 2 or 3 years later by Burke, Gerard, and Svetkov. Was to look at manifolds, to look at Strickard's estimates on manifold, and then you get a slightly different picture. See, in the picture of a compactly supported perturbation of Euclidean metric, each geodesic is good because it spends only this small time inside the variable coefficient region. So here you have no loss of derivatives. And in this context, you really have to do this decomposition in full and take the loss. You have no way of avoiding the loss. So here you have Strickard's estimates with loss. So this was maybe the story about 25 years ago. And then, of course, the question was, what if you want to have coefficients which are not constant outside the compact set? And there were a number of people who worked on that, including lots of people from the Paris area. So there are several results. Robbiano and Zuili. Then Hassel. This is not Paris area. Tao and Wunsch, and then also some work of Bouclet and Svetkov. So these were slightly different approaches which address the following situation. You have G, not a constant, not a compact perturbation of the Euclidean metric, but instead you assume that G is asymptotically flat. When you do this, you also have to worry about something else. You have to make your metric non-trapping. This is something that I mentioned earlier. And you look at these results locally in time. All right? So this happened around more or less 2005. So this is nice, but you would also want to have results which are global in time. And global in time, it's yet another layer of difficulty. And so this is work that I did, and work that I did with Marzola and Metcalf. So this maybe it was about 07. So this is kind of similar with some improved regularity of the metric. So this is where we get to C2 matrix. I think we also had C2 matrix with Gigliola over there. And then this is globally in time. And so the difference between these two papers, the first one had some smallness condition, which automatically guaranteed the non-trapping, and the second one required some quantitative version of non-trapping, expressed using local energy decay estimates, but I don't want to get into that. All right, so what's the secret here? One of the secrets, at least. You still want to have your wave packet parametrices, but you want to have the wave packet parametrices maybe in a more general context. And the way we are able to phrase the problem more generally, suppose we want, exactly like in the Schrödinger case, suppose we want wave packets with the spatial scale, the frequency scale 1, the spatial scale 1, and time scale 1, right? And we look at, if you want a microlocal evolution, or here you put some pseudo-differential operator, and then you ask the question, what kind of conditions do you need to impose on this pseudo-differential operator in order for our parametric construction to work? And so if you write the Hamilton flow in here, is x dot is equal to xi, xi dot is equal to minus ax. If you want to go from time 0 to time 1, you'd better hope that this Hamilton flow is by Lipschitz from time 0 to time 1. And to study the by-Lipschitz property of this flow, you look at its linearization. And when you linearize the flow, you need to involve two derivatives of the symbol A. And so to make a long story short, at the time, I ended up looking at symbols which have the following property. So maybe you're familiar with this class S000. And then you sneak in a number 2 in here. What does this 2 mean? It means that when I look at dx alpha, d psi beta of A, this is smaller than C alpha beta. So that's the class S0, 0, 0, the classical class, for which, by the way, the Calderon-Vaillancourt theorem applies. But now we ask for this when alpha plus beta is greater than or equal to 2 only. So that's that 2 that I put in here. All right? So we don't care about the size of the symbol and its derivatives. We care only about the size of the symbols of the derivatives of order 2 and higher. And you can fiddle with this result. You can formulate different versions of this when you change the scales. And when you change the time, it's just a rescaling process. All right. And so the result says that if you have symbol, real symbol of this type, and maybe to make things simple, do the Weil quantization, then you have a wave packet parametrics, if you want, for this flow. This has nothing to do with dispersive estimates, because these assumptions do not tell you that the flow here is dispersive. So if you want dispersive estimates, you have to also put some condition that guarantees that the flow is dispersive. This condition in here, if you want, guarantees that the flow is by Lipschitz and that you have a wave packet parametrics. And then an observation that we made maybe 2 or 3 years later, which at the time we did it because we could, and there was perhaps no absolutely compelling reason to do it, and turned out to be life-saving years later, is that, you know, when you look at the linearized flow in here, you look at 2 derivatives of A, all right, and then you have to integrate 2 derivatives of A. Obviously, you can integrate 2 derivatives of A if they're bounded, but there's more functions that can be integrated which are not bounded. And an example would be to look at functions which are in L1, all right? So you might say, well, perhaps I should put A in L1 in T with values in S0, 2, 0, 0. Except that when you look at this wave packets, one wave packet doesn't see much of another wave packet. Whereas in here, you impose some sort of uniformity in X for each T. So you're giving away something. You're imposing some uniformity that you have no need for. So strike this out. And instead, what we end up looking is a condition on this same expression, dx alpha dxi beta of A, integral from 0 to 1, xt xi t. So xt xi t denotes the Hamilton flow associated to the symbol A. So we ask for this integral condition instead, separately on each bicharacteristic. All right?
It's integrating in time.
Say it again?
It's integrating in time.
Integrating in time. Yeah. And so the contention, this was work also with Jeremy Marzola and Jason Metcalf, says that if you have this condition, then you have a wave packet parametrics. Parametrics means you have a way of representing solutions as superpositions of wave packets. All right. So maybe the original version is a bit hard to find because, well, just like here, there were some lectures that I gave about 20 years ago at some summer school in Pisa, and they got published in some proceedings, which is a little bit hard to find. But you can find those notes also on my web page. All right. So this is our story so far, and you see that is not a very pretty picture when you try to look at Strickard's estimates for the Schrödinger equation. You need a lot of regularity, C2 regularity, maybe a little bit less than C2 because you have this integrability condition in time. But in X, you look at two derivatives anyway. And then you have this semi-classical time, which gives you losses when you try to get Strickhardt estimates for variable coefficients. So let's compare a little bit with the setup of our problem here, where we needed the Strickhardt estimates. So
can I have a question? Because probably I'm confusing two things. So in the first lecture, you mentioned this wave packet. The Strickhardt is not efficient once the wave packet is destroyed.
yeah.
So there was this time of lambda minus 2, and so the distance scale, so the uncertainty scale is lambda minus 1 here.
Wait. So it all depends on what you choose the time scale, right? For each time scale, you have two parameters. You have the frequency parameter and the time scale, right? So I might say for each frequency scale and each time scale, you have a wave packet scale. And that also depends on how strong your dispersion is. If you look at the pictures that I have drawn in here, and I was about to erase for the Schrödinger equation, if you want to go to time 1 with wave packets, and with the Schrödinger dispersion relation, it doesn't matter what your frequency lambda is, your wave packets have to be scale 1. For the Schrödinger equation, the only way I get to change that scale is when I change the time. And then I make the packets narrower if the time is smaller and wider if the time is larger. It doesn't, for the Schrödinger, the wave packet scale does not depend very much on the wave packet. The lambda that I had there in the first lecture was a different lambda. In that lecture, I had my wave packets, wherever I wrote I had the coherent states of the form x minus x0, all right? So there, the spatial scale was lambda inverse, right? And then by duality, by uncertainty principle, the frequency scale was lambda, and then the time scale is lambda minus 2. So the spatial scale is the square root of the time scale. Here we did things backward. We started with the time scale, and we figured out what is the wave packet scale.
Yeah, okay, but this is the same thing, right?
This is the same thing, yeah.
And yeah, no, I was just wondering about this. That this time is bigger, right? Than this. I mean, if I think about lambda as a frequency.
If lambda is the frequency,
then if lambda is large, that it's.
You're talking about the semi-classical scale.
Yeah.
The semi-classical scale is tiny, right? It's lambda inverse. It's much smaller than 1. But this is not the same lambda.
Yeah,
okay.
Yeah. Okay, so it has nothing to do, right?
Right.
Because then if
I have to get the notations right, and I did not think of matching notations from lecture 1 to lecture 4.
Yeah, no, I don't know, because I understood this as a heuristic argument that at scale lambda, Strickhardt is not very efficient after time scale lambda minus 2.
Exactly, but those are spatial scales. Frequency scale lambda, yeah. And so then. But there we're not at frequency scale lambda, right? If let's do the numbers here. If delta t is lambda inverse, then delta x is the square root of that, so that's lambda to the power minus 1/2, and then delta xi would be lambda to the power 1/2. So if I were to construct wave packets according to this predicament, the wave packets will have this frequency localization and this spatial localization. So they'll be very thin and then wider in frequency, but not as wide as my frequency scale lambda, right? There is, at frequency scale lambda, a decomposition in the Fourier space on the scale lambda minus 1/2 into lots of little cubes. All right, so we saw that we have some thresholds which are hard to cross, the C2 threshold and then the semi-classical threshold. And on the other hand, looking at this problem in here, we work with metrics. If you remember the local well-posedness results that I was telling you about, they work for U in HS, where S is greater than n plus 1 over 2. All right. So if I try to measure the regularity of the metric G in terms of Holder norms, you use Sobolev embeddings, and the best thing you could get is G is the 1/2 plus. So the metrics that we want to work with in here are much rougher than the technology that we had before. All right? And very likely, it's impossible to even reach at all this kind of thresholds for metrics which just have this kind of regularity. Instead, we want to say we have special metrics which come from an equation and take advantage of that. All right. So now I'll begin to tell you the story of the estimates in one dimension. So in one dimension, the contention was that we had Strickard's estimates without loss for the paradifferential problem. And I want to write down those estimates. So maybe if I want to write down the Strickard space in one dimension, I have two interesting norms: the energy norm L infinity L2 and the Petcher norm L4 L infinity, and then I can interpolate between them and I get all my Strickard's indices. If I put together these norms intersecting the spaces, is what I might call the Strickard space. And if I want to write down a Strickard's estimate without loss for this inhomogeneous problem that you have in here, that could be something like norm of U in the Strickard space smaller than norm of U0 in L2 plus norm of U lambda, U0 lambda, F lambda in the dual Strickard's space. So you might say, okay, so this is already a lot to ask given the difficulties that we have. But then I'm going to turn around and say, oh, but this is actually not enough for what we need. It's not enough for what we need because the source terms F lambda that we have for the paradifferential equation are obtained by throwing everything else in the nonlinear equation on the right-hand side. So they are pretty bad. And there's no way we could put them in any sort of this kind of Strickard space. And so even if we were able to prove this, it would be useless to us. Okay? And so what happened was that what we realized is that we have to enlarge the space of source terms we allow in here. So we want to make this space a little bit bigger and make it a little bit bigger in such a way that all the source terms that we have to put in here will fit in this box in here. I'm putting the new box in here so that my source terms from there will fit inside this box, and then hope that we can still prove this sharper version of the Strickard's estimates. Let me give a name to this box. X star. And let me tell you what this X star is, because this is one of the important pieces of information in here. And this is one of those rare instances when you have a problem And that problem turns out to be part of the solution, in effect. So without adding this, we would not have been able to prove the rest, in other words. And so what is this X star norm? Well, if we just try to get energy estimates for a problem like this, and you compute ddt norm of V lambda in L2 square, this is 2 times the real part of, and here maybe, let me write this in divergence form so that this energy estimate is cleaner. This is 2 real part of F lambda V lambda integrated. So if all I want is energy estimates, I need to be able to estimate this integral. And that made us consider this expression I of V lambda F lambda, which would be, so you'd like to look at F lambda and times V lambda in L1. That would allow us to estimate this. But then you also want to do other, let's say, frequency localizations and this kind of manipulations. So instead of just looking at this, we allow us to have a translation parameter in here. And you take a supremum over x0 in R. All right. And now we define the norm of V lambda in X. Define X by the following: V lambda of 0 in L2 plus square I of V lambda F lambda. So I choose to measure solutions to the inhomogeneous equation in this way. There's multiple reasons to make this choice. One sort of trivial reason to make this choice is that this choice guarantees energy estimates. But the most important reason to make this choice is that making such a choice is what's necessary for the bilinear estimates that I was telling you about last time. So this allows this us to prove bilinear estimates using the interaction Moravec's ideas. All right, so I would like to measure a function V lambda like this, and maybe let me change the notations a little bit, because my V lambda, I don't want it to be exactly the V in the paradifferential equation over there. And instead I want this W to be a solution to the adjoint equation, which happens to be the same as the original equation. But just to emphasize this is the adjoint equation, let me put the time t in here. Suppose all the action happens in some time interval 0t. So the original equation, let's say, just for convenience, we solve it forward on time, in time from time 0 to time t. And then you have an adjoint equation which looks the same like this. But now we solve that backward from time t to time 0. It's equivalent if I put here t or 0. In any case, I refer to this as a norm. This is not a norm, just a functional, but it's a non-negative functional. And one can fiddle with this and try to turn it into a norm. Can be done. It's work and is unnecessary. And now I use this X to define X star, which is now a norm space, a Banach space. So I define norm of F lambda in X star to be equal to supremum, let's say, of a norm of F lambda W lambda in L1 when norm of W lambda in X is smaller than or equal to 1. This is still homogeneous, so it makes sense to compare it to 1. So this, if
so is there a square on the I?
when you define it?
No, because I is already quadratic. It has two variables in it. It has your solution and the source term. So as far as homogeneity is concerned, I is at the same homogeneity as V square. So that's why we don't need the square over here. That's why I put squares here and here. So I think if X was a norm, then this would define the dual norm, right? But X is not a norm. All right. And so that's how we define this X dual.
Another question. So the X depends on F lambda in a way.
F lambda is part of V.
Now it's G. So we have V with F and W with G, right? So different objects. Sorry, bad notation on my side. All right.
But G is not the metric.
Hmm? H. Think of that G as H. That's instructions for you. Right, not the metric. All right, so let me tell you right off the bat what are some advantages, even if you don't think of the nonlinear equations, what are some advantages in putting that X star over there, in making the space of source terms bigger. And one advantage is that it allows us to change, so X star allows us to change the equation. And this is something in terms of Strickard's estimates. This is a game that maybe many of you have played. You have an equation, lots of terms. Maybe some of those terms are perturbative. You try to throw them away, right? And it's the same kind of game in here. So our original operator is, let's say, G of U less than lambda times D times D. That's the guy that we want Strickard's estimates for. And then the first minor change, you could say, that we do to this guy is we say, well, perhaps I can localize the metric G a little bit better in frequency. And the reason I want to localize G a little bit better in frequency is that I want to make sure that G doesn't take us outside of the lambda region too quickly. So I want to replace this by dg of U lambda to the power sigma d. And here sigma is smaller than 1, but very close to 1. We have a little bit of leeway in there. All right. The next way we can change our operator is now plus, I want to add a magnetic potential and a potential in here. And I want to say, well, if I play my cards right, I have nice classes of magnetic potentials and potentials which I can add for free, perturbatively. Okay? Now, what are the classes of potentials and magnetic potentials that I can add for free? And let's think first of all about potentials in here. There is an obvious choice to make. If you look at the estimates, you might want potentials that map S into S prime by multiplication. Those would be perturbative in the Strickard's inequalities. That would be the trivial choice to make, which doesn't work for us. All right? But, so one choice maybe. What V? Let's worry about V because that's the bad guy, not the W. So I said we want to go from S to S prime, but in the case of V, we also need to defeat this derivative, which is like a factor of lambda. So one possibility in here, naive possibility, is V is in lambda inverse. And I'll write something that's completely wrong, but you'll get what I mean. S divided by S prime, right? In other words, V multiplied by S takes us into S prime, right? So this will be some LP guy, all right? And think of this as my backup option. Everything that doesn't go into my main thing, which I'm going to tell you now what it is, I'll try to throw it in there, and it works. All right, and now the main thing takes advantage of the fact that our metric comes from our Schrödinger equation, and that our metric is quadratic. Remember, our equation was cubic, so the metric was at least quadratic. So this G of U less than lambda, you should think about it at least as U less than lambda square plus the identity. So identity we don't care about. We care about this guy, all right? And so you have two low frequency copies of U. And so that will eventually be important in our choice of this potentials V. And the choice we're going to have in here is to look at potentials. We also want to bound them in a pointwise way. And naively, you might say, I want to bound these potentials by G lambda sigma, U less lambda to the power sigma times U less than lambda to the power sigma. So two copies of my metric. Oh, I forgot to put derivatives, so these are differentiated. Okay. Well, first of all, why does this work? Obviously, the contribution of this component of V, I cannot estimate it using the Strickhart's norms. So the way to estimate the contribution of this V is to use this X star norm. So the way it works is, suppose I want to estimate norm of V times derivative of whatever we have in there, U in X star. So I take the supremum of norm of V times derivative U lambda times W lambda in L1. All right, W lambda is my test function from the definition of the X norm. This V has these two components, U much less than lambda. Maybe it has more, but it has at least two copies of this. And now I have a quadrilinear expression. I put terms 2 and 2. I have two unbalanced interactions, one here and one here. And for each of these unbalanced interactions, I can hit them with my bilinear L2 estimates, which came from interaction Moravec. So I'm going to estimate this product in L2, this product in L2, together in L1. So that's why this V is good. All right. Now, we want this to be invariant with respect to translations. So simply putting this does not work. And instead I'll borrow a notation from Tao. And instead of looking at these guys, I'm going to think of a bilinear form in this. I don't know how many of you are familiar with this notation. So this simply means that I have a translation invariant bilinear form with an integrable kernel. So I can think of this L of this and this as a superposition of products of this and translates of this, if you want. Okay? So it's like putting the product, but allowing myself to have arbitrary translations of either of the two factors. That's the idea. All right. Maybe now it's a good time to stop because I'll switch gears in a second, and then maybe we take a 5-minute break now. Okay, so to continue, I've been telling you that we could add these potentials. I didn't give you any clue why we would care about adding these potentials, and what should these potentials be. So this is a little bit like after the fact that we notice that we need to do this. And now we come to the place that will lead us to the need for these potentials, and also to the reason why this actually works in one dimension. And this is something that will not work in higher dimensions. So one special thing about one dimension is if you have a metric on the real line, then you can make a change of coordinates to turn this metric into a flat metric. All right? So you can change coordinates. Let's say y is the antiderivative of something like g to the power minus 1/2 dx. New coordinate. So you go from x to y, and then the dg dx g dx will turn into dy2, second derivative in y. And so if you do a change of coordinates, then your metric becomes flat. Okay, so this is not a new idea, obviously. And in effect, even for this one-dimensional Schrödinger equation, it was used maybe 20 years ago by Burke and Planchon to prove that Strickard's estimates hold for BV metrics in one dimension. All right, you just turn your problem into a constant coefficient problem. Unfortunately, what they did has no chance of working here because they looked at the situation where you have a metric that does not depend on time. Okay? In our situation here, our metric depends a lot on time because it comes from the solution to some PDE. There's no way we can freeze the metric and make it independent of time. Okay? So, you make the change of variables, your metric becomes flat, but then you end up with extra terms in the equation. So you are essentially trading one problem with another. So our equation there turns into I dt plus dy2 plus some potential dy. That would be the idea. And what is this potential? It has two components. One component comes from the time derivative of the metric. Maybe with an I, because dt comes with an I. And the other component comes from commuting metric with the derivatives, so an x derivative of the metric, more or less. Okay? You can imagine by glancing at these two terms that exactly one of them is the bad guy, which is this one, right? Time derivative of the metric, because the metric solves an equation, well, is a function, so g is g of u. U solves an equation. If I apply derivatives with respect to time in u, I get two derivatives of u. So I could say, oh, this is really bad, I give up, right? No, you don't give up, you try to see what you can do with that. So maybe I have to write down what is this time derivative of g, and I'll try to give you a quick idea how that goes. let's see, I can erase here. So if you write down the bad component coming from dtg, you get something like this. You get, well, when you look at y as a function of x, that's not dt of g. I misspoke. Is dt is dy dt, like chain rule. And we want to do this guy. This y will depend on the metric g, but there's an intermediate integration involved in this. So if you look at dy dt, this is an antiderivative of dt of g to the power minus 1/2. And this is less than lambda to the power sigma dx. All right. Okay, this is a power. You apply chain rule. This derivative would, let's think of this g as quadratic. So let's think of this as u square. The constant component in g dies under differentiation. So you have the quadratic portion that's left. So this will be morally like integral of dt of u much less than lambda sigma times u much less than lambda sigma. You take two derivatives of your solution. That's the bad guy. One time derivative, that's two spatial derivatives, right? So this is like integral of dx2 u much less than lambda to the power sigma times u much less than lambda to the power sigma, right? And we still have the two derivatives, right? But good news, this gets integrated. So as much as I promised no integration by parts, here we do one integration by parts, all right? So this gives us something that looks like dx u much less than lambda sigma times u much less than lambda sigma. And now you can almost see where I'm going. This is a good guy. This guy is kind of like my good V's in here. Even they are missing one derivative, so it's even better. All right, but plus, and now comes the really bad guy, the real bad guy, which is the integral of du much less than lambda to the power sigma times du much less than lambda to the power sigma. This is dx. And of course, in the computations that I'm doing here, I've been lying a lot. One place I've been lying is that when I am applying time derivative of the low frequencies of u, I also only get low frequencies of u in return. That's not true. The equation doesn't tell me that. Doesn't keep frequency localization, so we also get contributions from higher frequencies. You have to estimate that. I'm hiding that under the rug. Okay.
Sorry. Also, it's g that is morally u squared, so then you have g to the negative 1/2.
The negative 1/2 doesn't matter. I do chain rule, I get the power of g.
And then you just bound it.
Yeah. That's just bounded by a constant. Right. Another of the things I'm hiding quickly. Okay, so we end up with this guy in here. And you could say, well, I have this integration. Is this good or bad? In terms of regularity, integration is good, right? Because it makes things more regular. But in terms of size, integration is bad. Because if you take a function and you compute its antiderivative, there's no way that antiderivative is going to have any sort of decay left in it, right? So neither good nor bad, sort of mixed news in there. And then what do we do with this guy? we would like to put it in this V in here, but we can't quite do it because in this V in here, implicitly there is some decay. These guys are decaying at infinity. This one doesn't decay at all because of the integration. Okay? So what do we do with this guy? We take this integral and we split it into two parts using spectral projectors. One part, we project it to frequencies less than 1 in the y variable. And then the other part, we project it to frequencies larger than 1 in the y variable, using a smooth partition of unity in the Fourier space. And now, we're trying to decide what to do with these two pieces. This is also with the integral. So here I'm integrating, but I'm integrating something that's at frequency larger than 1. This is harmless, right? This gives me morally an integrable kernel. Well, it does give me an integrable kernel. And so this guy, I will put it in my V in here. Okay. Check. Now what do we do with this other guy? This has the low frequencies in it, and this is the guy that has no decay. And then we put this guy in the box that does not require decay. So if all I'm left is with this guy inside of my symbol in here, then I'm looking at the symbol A of x psi to be A of y and psi. Y, well, it's in the y variable, is psi square plus p less than 1, if you want, v times psi, right? Something like this. And remember that the unit scale was the key scale for the wave packet parametrics that I was telling, for the Schrödinger parametrics that I was telling you about. Well, this happens to be exactly at the unit scale. All right? And so it's perfect, right? So I'll try to take this object in here and put it inside of my wave packet parametrics. And so I'm getting to the punchline in here, nearly. Because what I will have to estimate is the integral of derivatives of these symbols along the geodesics. So I'm looking at integral, and most terms are good. Let me just take one derivative coming in here. Okay, or maybe two derivatives coming in there. One or two makes no difference because this is localized to frequency smaller than 1. So each derivative is smaller than 1. Okay, so I'd be looking at p less than 1 dx of v times lambda. Xi is my frequency factor, which is of size lambda. And this is integral from 0 to 1 in time. And this is the evaluated at xt psi t. So this is along the Hamilton flow, absolute value, dt. So I have a bad factor of lambda, all right? But lambda times dt, our geodesics move with velocity lambda, so lambda times dt is like dx. Right? The picture that you should have in mind is I have time 0, time 1. I have this geodesics that move very fast. They move with the group velocity lambda. Okay? And then dt and dx are related by factor of lambda. So this lambda goes in here. And then we end up with the integral of our geodesic gamma of p less than 1. And when I differentiate with respect to x, I get to kill this integral, okay? And then I'm left with something that looks like du much less than lambda square ds with respect to the arc length on the geodesic. All right? So I'm looking over this geodesic, and I'm trying to estimate the low frequency portion of the solution, its derivative in L2. Okay, seems hard. However, U solves the Schrödinger equation. It's at frequency less than lambda, much less than lambda, so it moves with the group velocity much less than lambda. So this means that when I'm looking at how U, my solution to the Schrödinger equation, moves relative to this curve, it moves transversally. This is my U moving. It cannot move tangentially. That would be the enemy, right? If I had some portion of U that moves along this ray, that would make for a huge integral. I don't want that. I know that U moves transversally. So from the perspective of this U in here, this geodesic, it's almost like an initial surface. Okay? If this were a wave equation, I would say it's space-like relative to these low frequencies of U. So really what I'm doing in here, I'm estimating the H1 norm of what you might call the initial data for U less than lambda. So this would be comparable to norm of U less than lambda in H1, right? It's not that constant time, it's on this curve. But this curve, from the perspective of this wave, it's almost like constant time. Okay? And so this means that we can estimate these guys. And that's the punchline here. Even better than this, if we try to estimate gradient of U square on this curve, we didn't even have to work hard at all, because we have those density flux relations for U. So for instance, we know that if we look at the time derivative of, let's say, U mu square, this is the x derivative of some momentum plus some source term. And so in order to estimate this, all I have to do is to take my density flux relation and integrate it in a domain like this. And so at time 0, I get my initial data. On this curve, I get, let me put the derivative, I get derivative of U square. And then inside this region, I get the contribution from the source term, which is in L1. And that's, in a nutshell, what is happening. All right, so to summarize the argument for U, we take our problem in the original coordinates, we flatten the metric. When we flatten the metric, we end up with this bad gradient potential. We take the gradient potential and we split it in two. One portion goes into the perturbative box for a very carefully designed definition of what is the perturbative box. The other portion goes into the wave packet parametrics that I built many years ago with Jeremy and Jason. So in this work with Mihaela, we were able to use that parametrics out of the box. We didn't have to change it in any way. Very fortunate. That otherwise would have made the paper so much longer. And there's lots of details, lots of things that I have skipped, but this is, in a nutshell, how the argument goes in one dimension. And it relies, in a way, essentially on the fact that you can flatten the metric if you can handle the big losses that you take when you flatten the metric.
And again, you're interested in estimating this integral because you want your new symbol, let's say, to give you...
I'm interested in...
Floated this by Lipschitz.
Yeah, I'm interested in estimating this integral because I want my symbol to have a wave packet parametrics and therefore to have dispersive estimates. Yeah, what I was saying in the beginning. So this is where the story connects with my story from the beginning. All right, so in a nutshell, this is what happens in one dimension. And now I have half an hour left to give you an idea of what happens in 2 dimensions and higher. And now that you have seen the story in 1 dimension, you will see that the story in 2 dimensions and higher is a little bit simpler. So what doesn't happen anymore in 2 dimensions is you have a metric in R2 or in Rn. You cannot make a change of coordinates to flatten it, right? And so you might say perhaps you don't need to flatten the metric. All you need is to gain enough regularity to use that wave packet parametrics. That's still very far from what we can do. All right, let's see, where do I go for 2 dimensions? Maybe I'll keep that. Let me go here. All right, so our theorem in 2 dimensions. So this is with Mihaela, and is part of our paper on the quasi-linear Schrödinger equations in 2 dimensions and higher. This says that if I'm trying to look at that paradifferential equation, and I try to estimate norm of, let's say, V lambda in LP LQ, I can estimate this in terms of norm of V lambda of 0 in L2 plus norm of F lambda. And now I want to see where I put this F lambda. You might say this should be a Strickart space, but instead of the Strickart space, here we'll go straight to some space like our X star from before. The reason we want to enlarge the space of the source terms is because we have exactly the same problem as before. The source terms we need to deal with come from the nonlinear equation. We have thrown a lot of terms inside this box, and we need to be able to estimate the terms inside this box. That's why we need a very big box in here. But this is not the same as in 1 dimension, and I'll tell you in a moment why. And this has a loss of derivatives, lambda to the power minus 2 over p, very exactly quantified. The spaces that we're putting in here actually depend on whether you're in dimension 2 or 3 and higher. This is a technical difference. In dimension 2, you have that forbidden endpoint. And that causes a little bit of hardship, but nothing serious. So in dimension 2, this space, well, I'll get in a moment to what we want to put in here. Let's see. Trying to decide how much detail I have time to go into. So this norm in here, if I think about it at least in 3 dimensions and higher, I can, let's say if I'm in 3 plus dimensions, I can interpolate it between 2 norms. I need to estimate norm of V lambda in the energy space, L infinity L2, and that does not have a loss of derivatives. And this is integration by parts. This is smaller than norm of V lambda of 0 in L2 plus I of V lambda F lambda power 1/2. The computation we did before, that was the motivation for introducing this quantity. And the other estimate that we have is norm of V lambda in L2. This would be 2n over n minus 2, smaller than norm of v lambda of 0 in L2 plus I of v lambda f lambda to the power 1/2. And this is what I put here on the right is no longer enough. That's basically enough to be able to close the energy estimate, but not the Strickhards. And then this would be a lambda inverse. And because I have a lambda inverse here, I can put a lambda inverse in here, norm of, and let me change the letter on you. This is n we used in this paper because it's a slightly different object, norm of f lambda in this space n. So this is where we need to estimate our source terms. But our source terms, we need to estimate them more carefully only in the setup where we have a loss of one derivative. So we have a loss of one derivative at the endpoint. We have a loss of no derivative of the energy estimate. And this, by interpolation, gives us this intermediate loss for the intermediate norms. Now, if you go in dimension 2, you lose this endpoint because it becomes L2L infinity. So in dimension 2, instead of this guy, we put what's called the V2 space. Okay, and I really don't have time to explain the V2 space. Maybe I said something about V2 in one of the other lectures. And then this source term in here is estimated in dV2. So maybe this U2 and V2 spaces come together. This is something from that I came up with maybe around 99 as a replacement for the Bourgain spaces in contexts where you want estimates in scale invariant function spaces, and the Bourgain spaces somehow were just not working all the way to scaling. All right. So this is just a slight variation that's forced on us because we're losing this endpoint. So our strategy here is considerably simpler than the strategy in the one-dimensional case. And that's because we're allowed to lose derivatives. So the strategy is we start with our equation, let's say, which is written in here. We take the metric G, and we try to replace the metric G with the identity. And in general, that's a bad idea because you cannot perturbatively change the metric to the identity and estimate the errors nicely. But still, we write our equation, I dt v lambda plus Laplacian v lambda is equal to f lambda plus, and then I have identity minus g much less than lambda. This gets multiplied by two derivatives of v lambda. And we're at frequency lambda, so these two derivatives are kind of like a factor of lambda square. Right? So, f lambda is the source term that we're given. And here the constraint is that this comes, in our application, this comes from the Schrödinger equation. So it's a big box, and that's why we have to introduce this, this kind of spaces. This expression in here we use the fact that the metric G is at least quadratic, identity plus at least quadratic. So this expression in here, just like in the one-dimensional setting, is like u much less than lambda times u much less than lambda. So you might say this is a good guy, right? Still, where do we take our Strickhardt estimates? Because we want to cheat a little bit and not have to prove new Strickhardt estimates. We take our Strickhardt estimates from the constant coefficient problem. But if we want to take our Strickhardt estimates from the constant coefficient problem, then we have to change the way we define this n-sharp norm. And now we define this n-sharp norm relying now on the constant coefficient problem. So this would be the supremum of norm of f lambda w lambda in L1 when norm of where w lambda solves I dt plus Laplacian w lambda is equal to, so now we can finally have the h lambda. I think in the paper we put g in there, I must say. All right. So it's a inhomogeneous Schrodinger equation. And the norms in here is we measure w lambda in the Strickart space plus h lambda in the dual Strickart space. So sort of a mild choice, if you want. And so we define our space of test functions as, if you want, Strickart solutions to the linear Schrodinger equation. And this is still is a pretty big space, comparable a little bit to the space that we had before. And the reason why this space is good is because I'd like to take this term in here and try to put it in this box, try to measure this in n star. Okay, and so what happens when we do this? We end up looking at the product u less than lambda, u less than lambda, times lambda square v lambda from here. And here we estimate this with the w, multiply this with the w lambda. And we want to estimate all of this product in L1 in order to be able to estimate this f lambda in n star. All right, and so it's the same story as I was telling you before in one dimension. We have two low frequencies, two high frequencies. We pair them 2 and 2, two unbalanced interactions. For each of these two unbalanced interactions, we apply the bilinear estimate. And here, there's something I mentioned when I was telling you about interaction Moravets and bilinear estimates. Namely that when you look at interaction Moravets, you have an easier scenario and a harder scenario. The easier scenario is the unbalanced scenario, where you have fast waves tested against slow waves. And that's the waves, there the waves are transversal to each other. And then it doesn't matter really along which flows they move. As long as they move with different but transversal flows, you can prove your estimates. And that's what happens when I test u less than lambda against w lambda, right? Because w lambda moves along the constant coefficient Schrodinger flow. U less than lambda moves along the variable coefficient Schrodinger flow. Okay? Here, this guy and this guy are closer friends, if you want. They move both according to the paradifferential flow. Still makes no difference. As long as you estimate unbalanced interactions, you're good. All right, so the argument that I showed you in here tells us that we can take the error from replacing the metric with the constant metric and estimate that perturbatively. Let me show you one last thing in terms of the number of derivatives. Here you have two derivatives, which is bad. You don't want to lose two derivatives. Every time you do a bilinear estimate, you gain half a derivative. So you gain half a derivative from here, half of derivative from the other bilinear estimate. Altogether, you have gained one derivative, subtracted from 2, you're left with the loss of one derivative, and then you get the loss of one derivative exactly in the endpoint estimate. And then you interpolate that with the energy, where you don't have any loss, and so you get intermediate losses at intermediate Strickart exponents. And maybe the last thing that I wanted to point out was that the place where we actually need to use the Strickart estimates in dimension n is equal to 2. And there we use the L4 bound to close our nonlinear Schrödinger argument. And so 4 is right in the middle between 2 and infinity. So in L4 we lose 1/2 a derivative. And interestingly enough, this loss of 1/2 of derivative is exactly perfect to give us the sharp global result, right? And maybe the last thing I would emphasize is that this theorem gives you global in time estimates, assuming that you have global in time solutions for the nonlinear Schrödinger equation. So it's part of the global bootstrap for the 2D global result. Okay, and so it was very important that we don't lose any more derivatives in the Strickhatz estimates than we lost. Otherwise, we'd have had something that's not sharp, and that's not good, right? All right, and I think this is a good time to stop, and maybe if there are questions, there's time for that. Well, there are lots of questions along the way.
Yes, that's true.
Part of the difficulty here is that there's this big setup, and it's important to make everything fit together. And you don't know till the very end if everything really fits together or not. Problem with the bootstrap arguments.
I actually had a couple of questions. One may be naive, but it's my ignorance. So what is the adjoint equation you were talking about?
So if you have where's the chalk? If you have a partial differential operator, well, if you have an evolution equation, maybe better, u prime is equal to au, u of 0 is equal to u0, then the adjoint equation would be v prime is equal to a star v, with v of t is equal to maybe vt, and then you have a duality relation between these two. Maybe we can also put source terms.
So all of this you were talking about, you did it with examples of the Schrödinger equation, the quasi-linear version, the quasi-linear version, and so on. Then what about wave equations, for instance?
Well, all the examples we have worked out so far are examples with full dispersion. And quite a few things go wrong when you try to do things with degenerate dispersion. So I don't know. Our last paper, if you want to take a look at it, from October, already you see in there how much harder it is to look at equations which are just not Schrödinger. So other dispersion relations, like I gave you some examples in the first lecture, is not at all easy to make the leap from Schrödinger to something else.
Let's say maybe my question would be, again, very general. What of all these could be saved for free, or I don't know.
What could be saved for free?
Meaning, all these stores that you told about, is there... I don't know, I actually don't really know what my question really is. I just wonder if there are, places where you know that things must be changed, that it's not going to work, and you have to, think of something completely different, compared to other places that you explain where, you take what you've done and it can be, maybe a similar argument can be done.
Right, so in some sense it seems like every departure from the setting that I've been talking about is non-trivial. It's non-trivial to change from Schrödinger to something else. It's non-trivial to, I don't know, allow your dispersion relation to degenerate. It's non-trivial to do lots of things. So,
and staying, for instance, with the Schrödinger equation, so this story that you told us about is for the scalar case. What if one wanted to consider a system of Schrödinger equations?
Well, so first of all, when you talk about systems, you might end up in a situation where different components of the system have different principal parts, and then you have different flows, and then it's hard to tell what's happening. So the easier case is when you have systems which use the same background metric, so to speak, or the same background operator, where all things tend to travel in the same direction, so to speak. And there, things might work in principle, but you have to have a good definition of what it means for your problem is to be defocusing. The definition that we provide is for scalar. So, I mean,
this is for postdocs, not for graduate students, maybe.
Maybe more than postdocs. No, absolutely.
What happens in the degenerate case?
What kind of degenerate case would you have in mind? What would degenerate?
I mean, when I have no scenario in mind, but when...
I mean, you can look at situations where dispersion degenerates. You could look at scenarios where the defocusing condition degenerates. And it's an open question. What happened?
I mean, you didn't work on this question.
Well, we have maybe as many of 6 projects going right now on various aspects of this problem, but I can tell you that degenerate problems are hard.
I'm not an expert, so thank you.
Somehow, but if I were to give priorities, I think quasi-linear problems are a greater priority than degenerate problems in some way. So that's where we've been looking at.
Okay, so we just have to thank Daniel again for the 4 lectures.